By the U.S. Geological Survey as very high threat volcanoes, Mount Hood, Mount St. Helens, and Mount Rainier.
The United States Geological Survey released a startling announcement after new satellite imaging revealed a vast network of subsurface magma tunnels linking Mount Rainier, Mount St. Helens, and Mount Hood. The findings stunned both geologists and the public because these mountains are not only iconic symbols of the Pacific Northwest, but also some of the most closely monitored volcanoes in North America. To detect connections beneath them suggests that they are not isolated volcanic giants, but components of a broader integrated magmatic system. This revelation has implications that stretch from geology and climatology to ecology and the human communities that surround these peaks. Before we start, smash the like and subscribe buttons for more updates. The Cascade Range has always carried an air of unpredictability. Mount St. Helens erupted catastrophically in 1980, an event that reshaped American perspectives on volcanic hazards. Rainier, towering above Seattle and Tacoma, has long been considered one of the most dangerous volcanoes in the continental United States, largely because of its massive ice cover and the potential for lahars. Mount Hood, with its commanding presence near Portland, has been active within the last 2 centuries and remains capable of future eruptions. For decades, scientists studied each volcano largely as a singular system, but satellite thermal imaging and gravimetric analysis now suggest that molten pathways deep in the crust connect these volcanoes in ways previously unconfirmed. The data show heat anomalies stretching between the volcanoes, resembling underground arteries, and their detection forces a re-evaluation of how magma moves in the Cascades. At the core of the discovery lies the concept of magma plumbing. Traditionally, each stratovolcano was thought to have its own chamber, fed by mantle sources from below. But the discovery of connecting tunnels means that magma can potentially migrate laterally across tens of miles. This has massive implications for volcanic activity because pressure buildups in one system could be relieved or aggravated by flows into another. For instance, if Rainier's chamber were to fill, some of that magma might escape towards St. Helens or Hood through these conduits. Conversely, activity at St. Helens might be fed not only by its own sources but also by input from Rainier's larger reservoir. This interconnectedness introduces complexity into eruption forecasting, as tremors or gas releases at one volcano may no longer be interpreted solely as localized phenomena. The very notion of magma tunnels brings up fascinating geological processes. These channels are not like open pipes, but rather zones of weakened rock, cracks, and semi-molten pathways where magma can squeeze and migrate. Over time, repeated intrusions carve out more permanent conduits. The satellite data picked up on subtle density changes in the crust, along with elevated thermal gradients that form a linear pattern between the 3 mountains. These features align almost like an underground highway system, suggesting that magma is not trapped in vertical columns beneath each volcano, but is part of a broader dynamic web. For volcanologists, this changes risk assessments, since the unrest of one volcano could now trigger or influence its neighbors. The Pacific Northwest tectonic setting makes this revelation particularly important. The Cascades are fueled by the subduction of the Juan de Fuca plate beneath the North American plate, a process that continually feeds magma into the crust. If the subduction zone is supplying material into a network instead of isolated pockets, the system's capacity for pressure buildup is far greater than previously imagined. That could mean larger eruptions are possible, or that eruption styles could be more varied, influenced by how magma mixes and migrates through the tunnels. A basaltic surge from deep sources, for example, might flow into a chamber of silica-rich magma, leading to explosive reactions. Such possibilities have long been modeled theoretically, but the confirmation of direct connections between major volcanoes provides the first real evidence of these scenarios. From an ecological standpoint, the presence of an interconnected magma network means the ground beneath vast stretches of the Cascades is far more alive than it appears. The forests, rivers, and valleys that seem stable are perched above a restless system of molten exchange. Even without eruptions, magma movement can cause uplift, seismic swarms, and hydrothermal alterations. Forests on the flanks of Rainier or Hood could see ground deformation, while underground aquifers may be heated or disrupted. Species that depend on delicate alpine ecosystems might find their habitats altered not by surface eruptions, but by the slow churning of the crust below. The interconnected system thus presents subtler long-term environmental shifts alongside dramatic volcanic hazards. The implications extend beyond natural sciences into human society. The urban centers of Seattle, Tacoma, and Portland are within range of hazards from Rainier, St. Helens, and Hood, respectively. An interconnected magma system means that emergency planning cannot simply focus on one volcano at a time. Authorities would need to consider chain reactions or simultaneous unrest. If, for example, seismic activity at Rainier caused magma to surge towards St. Helens, it could create unrest there as well, leading to unpredictable sequences. Evacuation strategies would have to be adaptive, and monitoring systems would require greater integration. Local economies, heavily tied to tourism, outdoor recreation, and agriculture, would face heightened uncertainty. The mental weight of knowing that 3 iconic peaks are connected deep below could reshape how people in the Northwest view their landscape. For geophysicists, the discovery validates the power of satellite imaging. Ground-based monitoring can pick up tremors and gas emissions, but only orbital perspectives can reveal large-scale density patterns and thermal anomalies across such vast terrain. The data that revealed these tunnels did not come from a single snapshot, but from years of accumulated measurements, refined by increasingly precise instruments. This demonstrates the growing role of space-based observation in Earth sciences. Satellites now function as extensions of seismographs and GPS arrays, offering holistic pictures of Earth's crustal activity. The revelation about the Cascades shows that even in one of the most studied volcanic arcs on the planet, surprises remain hidden until technology advances enough to uncover them. The existence of magma tunnels also changes how scientists model the history of these volcanoes. Rainier, St. Helens, and Hood have erupted on varying timelines, with St. Helens famously erupting in 1980, Hood showing activity in the 1800s, and Rainier last erupting in the late 19th century. Previously, these timelines were treated as largely independent, but if magma moves between them, past eruptions may have influenced one another. The buildup at St. Helens in the late 20th century could have drawn from Rainier's system, and earlier events at Hood might have impacted Rainier's subsurface conditions. A re-evaluation of historical eruption records with this new context could reveal patterns that were invisible before. The interconnectedness could mean the Cascade volcanoes act less like individual actors and more like members of an orchestra, each playing off the others in unseen rhythms. One of the most striking consequences of the discovery is psychological. For residents of the Pacific Northwest, the mountains have always been both majestic and menacing. They define skylines, inspire artists, and attract adventurers, yet they carry the weight of potential catastrophe. To learn that these giants are connected underground transforms them from isolated sentinels into a single vast organism. The metaphor of veins and arteries comes naturally. Magma as blood, the crust as flesh, and the volcanoes as vital organs of a geological body. This shifts perception from localized threats to a regional identity shaped by shared geologic life. The people living between these mountains are not neighbors to 3 separate volcanoes, but residents atop one sprawling volcanic system. The scientific challenge now is to determine the extent and capacity of the tunnels. How much magma can they actually transport? Are they wide, stable pathways or narrow, shifting fractures that open and close over time? Do they allow for constant flow or only act during periods of heightened pressure? To answer these questions, researchers will deploy denser seismic networks, ground-penetrating radar, and magnetotelluric surveys. Every tremor and every gas vent will be reinterpreted through the lens of connectivity. For decades, seismic swarms near St. Helens were treated as localized precursors. Now, any activity there might also signify movement from Rainier or Hood. Monitoring thus requires broader spatial awareness and new computational models capable of simulating multi-volcano dynamics. The energy within these tunnels also raises intriguing possibilities for geothermal exploration. The Cascades already have abundant hydrothermal systems, and the conformation of magma pathways hints at concentrated heat sources in unexpected places. While harnessing energy from active volcanic zones is risky, understanding the flow of heat underground may open opportunities for sustainable energy projects in peripheral regions. The economic implications are vast, though such efforts would have to carefully balance against safety concerns and environmental impacts. What is clear is that the subsurface network represents not only a hazard, but also a resource, if managed with foresight. The discovery of magma tunnels linking Rainier, St. Helens, and Hood has ignited an entirely new field of inquiry that extends beyond the immediate boundaries of geology. The realization that these mountains are connected beneath the surface means that the very fabric of the Pacific Northwest is shaped by unseen processes stretching across vast distances. The satellites that detected these tunnels have not only mapped out a new vision of volcanic connectivity, but also unveiled a reminder that our understanding of the Earth is still partial and often provisional. This moment represents one of those rare scientific revelations where old assumptions are overturned and the landscape itself seems to shift under human comprehension. One of the most profound aspects of this finding is the redefinition of scale. For centuries, people have viewed volcanoes as towering but localized entities, each with its own rise and fall of activity. With the identification of hidden magma tunnels, the narrative changes from a collection of isolated peaks to a continental-scale system operating as a unit. The scale of this underground activity cannot be overstated. Networks of molten channels potentially stretch for dozens of miles, linking chambers and distributing heat, gases, and molten rock across a region far larger than what meets the eye. The idea that activity in Washington could directly influence outcomes in Oregon highlights the extent to which natural systems transcend human borders and categories. This discovery also casts light on the unpredictability of volcanoes in ways that challenge current models. Forecasting eruptions relies on patterns, gas emissions, seismic swarms, ground deformation. But these indicators have always been tied to local conditions. Now scientists must grapple with the possibility that tremors under Rainier might reflect not only Rainier's own magma, but also a pulse moving from Hood, or vice versa. Such complexity means that prediction will require models that operate on a regional scale rather than a volcano-by-volcano basis. The challenge lies in developing monitoring systems capable of discerning whether a seismic event is a local anomaly or part of a broader chain reaction across multiple peaks. Culturally, this revelation infuses the Pacific Northwest with an even deeper mythic quality. Indigenous communities have long told stories of connections between mountains, stories in which the peaks are seen as family members, rivals, or allies. Oral traditions have often described relationships between Rainier, Hood, and St. Helens that mirror the connections now suggested by science. While geology operates in data and tectonics, these new findings echo the symbolic connections that were already present in the narratives of the land's first peoples. In this sense, the scientific discovery does not contradict cultural memory, but rather reinforces and deepens it, demonstrating once again how myth and geology often intertwine in unexpected ways. On a planetary scale, the discovery of interconnected magma tunnels raises comparisons with volcanic systems elsewhere in the world. Iceland, for example, is known for volcanic activity that spreads along fissures linking multiple volcanic centers. The East African Rift similarly shows evidence of magma plumbing stretching across large distances. By identifying such a system in the Cascades, scientists can now compare patterns across continents, seeking to understand whether such connections are common in volcanic arcs or unique to certain tectonic settings. The Cascades may become a case study not only for regional safety, but also for refining global models of how volcanic arcs function over geologic time. The presence of these tunnels also has implications for the pace of landscape evolution. Volcanoes are not static mountains. They are constantly reshaped by eruptions, collapses, and intrusions. If magma is capable of moving laterally across great distances, then eruptions may not only build one peak, but also contribute to the destabilization or reshaping of others. Valleys, river systems, and even glaciers may owe their contours to forces operating beneath multiple mountains at once. Over millennia, this kind of connectivity could explain why certain portions of the Cascades are marked by clustered activity, while others remain comparatively dormant. The network beneath Rainier, St. Helens, and Hood may represent just one visible portion of a far larger web still waiting to be mapped. In terms of scientific methodology, the discovery underscores the importance of interdisciplinary research. No single tool could have revealed these tunnels. It required the fusion of thermal imaging, gravity field analysis, and crustal deformation measurements to bring the picture into focus. The collaboration between orbital technologies and ground-based science demonstrates that breakthroughs often emerge from cross-pollination between fields. Geologists, Satellite engineers, seismologists, and data scientists all played roles in interpreting the signals. This points toward the future of Earth sciences, where the integration of remote sensing and computational modeling may reveal other hidden systems beneath seemingly ordinary landscapes. The energy of the tunnels also has implications for the chemistry of magma and the explosiveness of future eruptions. When magma travels through long pathways, it interacts with the surrounding rock, assimilates new materials, and cools or crystallizes in unpredictable ways. This means that eruptions fed by connected systems could involve mixtures of magma types, producing more explosive outcomes than single-source events. An eruption at Hood fed partially by Rainier's magma would not look the same as Hood erupting alone. Such interactions make the Cascades a laboratory for studying the chemistry of hybrid eruptions, events where magmas of different origins combine into something more volatile. Beyond science, the discovery resonates with the way humans imagine their relationship with the land. For residents of Portland, Seattle, or Tacoma, the mountains have always stood as monumental presences on the horizon, beautiful yet threatening. Learning that these mountains are connected below ground forces a reconsideration of that relationship. Instead of three separate guardians, the region now appears to rest upon a single body with multiple heads, a being whose moods and movements could ripple across the entire region. This recognition fosters both humility and unease, reminding people that human boundaries, cities, states, even national borders, mean little in the face of Earth's geologic unity. The revelation of tunnels also carries implications for water systems. Volcanoes exert strong influence on regional hydrology, shaping rivers and aquifers through both heat and deformation. If magma is moving laterally, then heat could spread beyond traditional volcanic zones, altering groundwater flows and potentially destabilizing slopes. Lahars, already a significant concern around Rainier, might become even less predictable if triggered not only by localized eruptions, but also by shifts initiated from miles away. The Columbia River watershed, which spans the region, may prove more susceptible to underground heating than once believed, with consequences for fisheries, agriculture, and communities dependent on stable water supplies. In the realm of risk communication, the challenge will be how to convey the seriousness of this discovery without inducing undue panic. The tunnels do not necessarily mean an eruption is imminent, but they do highlight a complexity that increases uncertainty. Communicating uncertainty is one of the hardest tasks for science, especially when lives and infrastructure are at stake. Authorities will need to frame the discovery not as a prophecy of disaster, but as an advance in understanding, one that allows for more sophisticated monitoring and preparation. The public, in turn, will need to accept that living in the shadow of these peaks means coexisting with a dynamic underground system that defies simple explanations. Educationally, the revelation offers a profound teaching moment. Students studying earth science can now learn about the Cascades not only as a chain of volcanoes, but as a living system beneath their feet. Field trips to Mount St. Helens or Rainier will carry new significance as teachers explain that the ground beneath is connected to mountains on the horizon. This shifts the narrative of geology from static memorization of rock types to a dynamic, unfolding drama of subterranean connections. In a world where climate and environmental change dominate discussions, the idea of underground connectivity offers a parallel lesson in the deep forces shaping the land. The revelation also forces reconsideration of infrastructure planning. Transportation corridors like Interstate 5 and Interstate 84, which pass near these volcanoes, may influence stability in areas once considered safe. The region's reliance on hydroelectric power, much of it generated in volcanic river valleys, may also need to account for shifting geothermal dynamics. The discovery is not simply academic. It bears directly on how millions of people move, work, and power their lives. Another fascinating implication lies in the biological realm. Microbial communities thrive in geothermal environments, feeding on minerals and heat in conditions hostile to most life. If magma tunnels spread heat across wide underground zones, they may be hosting extensive microbial ecosystems still unknown to science. Such life forms could provide insights into extremophiles, organisms that thrive under high temperature and pressure, offering analogs for potential life on other planets. Thus, the magma tunnels of the Cascades are not only geological phenomena, but also potential laboratories for astrobiology, hinting at what life might look like beneath the crust of Mars or the icy moons of Jupiter. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma tunnels linking Rainier St. Helens Hood? We want to hear from you. Thank you for watching and see you next time.